Okay, how's everybody doing? The TA notified me and said I put in the answer for problem 5 in the homework. I don't know. I messed up. So so anyway, I guess you guys will get credit for the last one. And then apparently I also numbered the problems wrong, so it goes like 1, 2, 2, 4, 5, and instead of 1, 2, 3, 4, 5. So my apologies. It should go 1, 2, 3, 4, 5. I promise I know how to count. Just I wrote the numbers wrong for the homework, and then yeah, apparently for the last problem, I guess I wrote the code. So we make the same mistakes. You have like 2 different files open, and one's supposed to be your solutions, and one's supposed to be the problems you release, and then they have like similar names, and you accidentally write the wrong thing in the wrong file, and you upload the wrong one. So yeah, that happened. But okay. But anyway, at least you should still take a look at the homework problem, because the idea is when you try out the homework problem yourself, there's some experience to be gained and whatnot, right? It's the difference between trying to cook in the kitchen versus watching somebody cook. So if you just look at my answer without thinking about it, you'll lose the bit of experience there. But anyway, on Tuesday we started talking Markov chains, and we said that the idea is we want to draw a sample. Well, just like everything else in this class, is we're avoiding the integrals, we're avoiding the mathematical analysis by taking random samples from the distribution. And on Tuesday I said sometimes we're in situations where taking getting the random sample is difficult, and we need to have an alternative way to get a sample, okay? And instead of trying to get samples that are IID, independent, identically distributed, we'll get samples that are dependent upon one another. And for that we have Markov chains, okay? So, we got Markov chains. Okay, this will help us get samples from a distribution. Okay, the values are dependent. Okay, and then we talked about the ergodic theorem, which basically said that if you let a Markov chain run long enough, okay, if the Markov chain is irreducible and aperiodic, and do we remember what those terms mean? Irreducible means from one state you can reach every other state. Aperiodic means basically any of the states can happen at within any time interval type of thing. If the chain is irreducible and aperiodic, it will eventually converge to its stationary distribution. Okay, the values are dependent, and then we'll say irreducible and aperiodic chains will eventually converge to its stationary distribution. Okay, stationary distribution, and this is with probability 1. Okay, and that's the ergodic theorem, right? And so we said, we looked at kind of a simple 2-state case. and then we said, you know, we want to design a Markov chain whose stationary distribution is the target distribution that we want, okay? We want to design a Markov chain, and when we say design a Markov chain, that means find the kind of transition matrix, transition kernel, that will have a stationary distribution equal to our desired target distribution. Okay, so we want to design a Markov chain that will have a stationary distribution equal to our desired target distribution. And we said one way, one solution to this is the Metropolis algorithm. The Metropolis algorithm gives us instructions for this kind of setting up the transition matrix, transition kernel, and if we follow the Metropolis algorithm, we will end up getting a Markov chain that has a stationary distribution equal to our desired target distribution. So this is, I think, where we left off, and I listed out kind of the rules of the Metropolis algorithm, and today we'll look at it a little bit more in depth. Okay, and so we said Metropolis algorithm is one way to get a Markov chain where the stationary distribution is equal to our target distribution. Okay, and the steps were kind of like this. Start at some arbitrary state. Okay, propose, and it has to be a symmetric proposal, which I didn't define last time. Propose a new state. Okay, so you propose a new state, and then maybe you go, maybe you don't. All right, so at the next step, you'll either go to the new state that you just proposed, or you'll stay put, okay? So at the next step, either go or stay, go to new state, or remain at current state. Okay, and then you go with probability equal to probability of the new state, basically in target PDF, divided by probability of the current state. In the target PDF, okay? And if you use that to decide whether to go or not, then the resulting Markov chain will have a stationary distribution equal to your target distribution. And if we have time, we can kind of look at the maybe a small proof or derivation of it. Okay. All right, is this all okay so far? Any questions? Okay, and so the example in our textbook and that we'll follow along in class is Island Hopping by the Politician. Okay, so we desire to visit each island proportional to its population. Okay, and so we have islands 1, 2, 3, 4, 5, 6, and 7. Okay, and so the population of island 1 is whatever 1,000, and the population here is 2,000 and 3,000, etc., and this one has population 7,000, and thus the probability is going to be equal to 1 over 28, 2 over 28, 3 over 28, to 7 over 28, right? Because the total population of all islands is 28,000, right? So okay, and and so this is what our Metropolis algorithm looks like. So you start at island, we'll say theta, right? And then we flip a coin to propose island theta plus 1 if heads. So this island theta plus 1 with probability equal to 0.5, propose island theta minus 1 with probability equal to 0.5. So we're going to propose the islands that way. And then what we do is we move with probability equal to the probability of the proposed island in our target PDF, which is this, right? Divided by the probability of the current island. Right? So if we are currently at island 4, and we propose, we get tails, so we propose island 3, right? Okay, so our we accept the proposal with probability equal to what? 3 over 28, because that's the probability of the island we proposed, divided by our current probability, the probability of our current island, 4 over 28, okay, which is just equal to 3/4. Is that okay? One thing you might notice is that because the over 28 appears in both the numerator and the denominator, we don't actually have to worry about it, okay? The purpose of this 1 over 28 is so that when we add up all the probabilities, they add up to 1, right? So it acts as a normalizing constant. And because the probability proposed and probability current will have the same normalizing constant, an advantage of the Metropolis algorithm is that you don't have to worry about calculating the normalizing constant. Okay? And if you can think back to Bayesian statistics, we often had we have the situation where the probability of the posterior distribution is the likelihood times the prior divided by the marginal probability, right? And that marginal probability serves as a normalizing constant, and I said that's often difficult to calculate, so we just say it's proportional to the numerator. And it turns out that's okay because we can ignore it here. We'll I'll write this out a little bit. I guess we can explore that concept a little bit later, but it'll come up again. Okay, so we'll accept this with probability 3/4. So we'll go there, okay, or not. On the other hand, let's say we're at island 4 and we propose island 5. What's the probability that we move? 1. We will go with probability 1 because the probability of the proposed island is higher than the probability of the current island. So that will give us a ratio greater than 1. So obviously you can't go with probability greater than 1. You just go with probability 1. Okay. So we'll say example. So current is theta equals 4. Flip heads. And then we get, so we propose island 5. Probability of moving will be equal to probability of propose divided by probability current. So we have 5 over 28 divided by 4 over 28, 5/4. So this is greater than 1. So we go, so we move with probability 1. Okay, and so I guess formally, we write kind of our transition probability is equal to the minimum between 1 and the probability of the proposed and the probability of the current. Okay, so it's we look at our proposed divided by the probability of the current, and if that's less than 1, that's what we use. And if it's greater than 1, then we go with probability 1. Okay. Let's just kind of explore this. And so let's look at kind of our transition probabilities, right? So we'll create our transition probability matrix, and this is part of your homework, okay? But I'll get you started, okay? So here's our current island, and we can start off at islands 1, 2, 3, 4, 5, 6, or 7, and we'll look at our proposed island, or not current, maybe not proposed, I'm sorry, next. Okay? And so let's just take a look at island 4, okay? Okay, and so if we're at island 4, is there any chance that we will end up at island 1 on the next turn? No, right? So from island 4 going to island 1 has a probability of 0. What about island 4 to going to island 2? Also probability 0. Island 4 going to island 6 is probability 0, has probability 0, and island 4 to going island 7 has probability 0. Because you're either going to, you flip a coin and you're either going to propose going to island 5 or propose going to island 3, or you might stay put. I mean, you're proposing one of the adjacent islands, and you might go there or you might stay put. So there's really only 3 possible locations that you'll be on the next turn, right? So, so we said, what is the probability of ending up at island 3 on the next turn? So this value is going to be, first of all, what do we have to get? We have to flip tails in order to propose island 3, right? So first we have to get probability of tails, and then once we flip tails, then it's going to be multiplied by the probability of, I guess, accepting the move. Okay, so it's going to be the probability of tails multiplied by the probability of accepting the move to island 3. So what's the probability of getting tails? 1/2, okay? And then what's the probability of accepting the move to island 3? This is going to be 3/28 divided by 4/28, right? This is, we move with probability of P proposed divided by P current, okay? So this is 1/2 times 3/4, so this is basically 3/8. So we have 0.375. Is that okay? All right, if we're at island 4, let's look at what's the probability that we end up at island 5 on the next turn. So this is going to be the probability of getting heads multiplied by the probability of kind of the accepting the move to island 5. Okay, what's the probability of accepting the move to island 5? 1, right? So this is, if we propose island 5, we're going to move with probability 1. So this is going to be 0.5 times 1. We will end up at island 5 with probability 0.5. Okay, and then ending up at island 4, well, I mean, there's one simple way is we just say everything has to add up to 1, so it has to be 0.125, okay? Or we could say, you know, there's a few ways we end up at island 4. Well, there's 2 ways. One is we flip tails and we multiply by the probability of rejecting the move plus the probability of heads, and we multiply by the probability of rejecting the move. Okay, so this is going to be 0.5 times 1/4 plus 0.5 times 0, right? If we flip heads, the probability of us rejecting the move is going to be 0. If we flip tails, the probability of us rejecting the move is going to be 1/4 because we have a 3/4 probability of accepting. So this ends up being 1/8. No surprise. 0.125. Okay, and then your homework, part of your homework, is to fill out the rest of the transition table. Here, let's take a look at island 7. Okay, let's say we're at island 7, so we have a probability of 0 everywhere. Okay, and then let's say, so right here I'm going to put in, okay, so now we're also going to look at island 7. So here I'm going to put in the probability of going from 7 to 6, and here we have the probability of going from 7 to 7. Okay, so what is the probability we transition from island 7 to island 6? What has to happen there? This is going to be the probability of tails multiplied by the probability of kind of accepting the move, right? So what's the probability of tails? 0.5. And what's the probability of accepting the move? 6/7, right? I mean, maybe 6/28 divided by 7/28, but because that 20/28 shows up in both places, it's fine. All right, so here, basically we have 3/7. 3/7 probability, okay? What about the probability of going from island 7 to island 7? Okay, so here it would be the probability of flipping heads times the probability of rejecting plus the probability of tails times the probability of rejecting. Right? Because that's the only way we end up back at our current island, is if we proposed something else and then we rejected it, right? So if we flip heads, technically we're proposing island 8, okay? But island 8 doesn't exist, so what's the probability of us accepting the move to island 8? 0, so the probability of us rejecting the island 8 proposal will be 1, okay? So the probability of heads will be 0.5 times 1 for rejecting the move to island 8, okay? And then the probability of getting tails and rejecting it will be 0.5 times what? 1 minus 6/7, so 1/7. That looks like a plus, but it's a multiplication. Okay, so we have 1/2 plus 1/14. So that's 8/14 or 4/7. All right, is this okay? All right, and then let's just see if we set up our transition probability matrix this way, will its stationary distribution be equal to our target distribution? Okay, so we will achieve kind of our stationary distribution pi, when pi times p is equal to pi, right? So this will happen. So let's just take a look at island 4 and island and see what happens, right? So just for one of the islands, okay, we have stationary t. So for let's say for island 4, we'll say equilibrium on the probability of leaving island 4 is equal to the probability of entering island 4. Okay, and so we have, I'm going to write the probability of 3 given 4. So this is the probability of going to island 3 given we are currently at island 4. And then we have probability of 4 given 4 is equal to 0.125, and this is the probability of going to island 4 given we are at island 4. Then we have the probability of 5 given 4, and this was 0.5. I guess maybe I should go back. And then here, let me if we just think, what is the probability of going to island 4 if we are at island 3? What is this? So this would be the probability of proposing 4 times the probability of accepting the proposal, right? Which will be 0.5 times the min of 1 times P proposed divided by P current. And so we have 0.5 times the min of 1 and 4 over 3. So we get 0.5 times 1.5, right? So if we're at island 3, the probability of going to 4 given we are at 3 is equal to 1/2. All right? Okay, so I have all of these things listed out. Okay, and so we will look at kind of we can have something called detailed balance. So not just we'll have equilibrium if everything leaving is equal to what's coming in, but we will achieve what's called detailed balance. This is kind of like a more specific version of equilibrium. If the probability of going from state A to state B is equal to the probability of state B to state A of going from state B to state A, okay? So we can just look at what is the probability of going from island 4 to island 3, okay? Versus the probability of going from island 3 to island 4. Okay, so the probability of going from island 4 to island 3 is going to be the probability of going to 3, given that you are at island 4, multiplied by the probability of being at island 4 in the first place. Right? So this is just the total probability. What's the probability that, a random person in this island system happens to be transitioning from island 4 to island 3? Okay? And so this is, the probability of going to 3, given you are at 4, times the probability of even being on island 4. Right? And over here, we have the probability of going from island 3 to island 4 multiplied by the probability of even being at island 3 in the first place. Is this okay? All right, so what is the probability of going to island 3 given you are at island 4? Earlier we said this was 0.375. And so we'll multiply this by the probability of island 4. And then over here we have probability of 0.5 times the probability of being on island 3. Okay? So when will these two equal? These are equal. Okay? So if we have detailed balance, then these two probabilities are equal. Right? So the probability of going to island 4 from island 3, we're going to say is equal to the probability of going to island 3 if you're at island 4. Okay, so if 20 people are going this way, then 20 people are going the other way, all right? And if that happens, then we are at equilibrium, okay? And so this, if we set these two equal to each other, then what do we get? We would get probability of island 4 needs to be times the island 3. Probability of island 4 needs to be equal to 4/3 the size of island 3. Okay, so this is achieved. Balance is achieved when the relative populations have this ratio. Okay, so we'll say island 4 needs to be 4/3 the size of island 3. Okay, and then and we can do the same thing to the relationship between island 4 and island 5. Okay, and we will find a similar setting. Okay, we'll find that island 5 needs to be 5/4 the size of island 4, which needs to be 4/3 the size of island 3. So you'll see that island 5 needs to be 5/3 the size of island 3. Okay, and this can be applied, and you could find out the relationship between all of the islands. And when we do that, we will find that only the target distribution will satisfy all of these kind of stationary criteria, right? So in the target distribution, island 4 is indeed 4/3 the size of island 3. Island 4 has a population of 4,000. Island 3 has a population of 3,000. Island 4 has a probability of 4/28. Island 3 has a population of 3/28. And we could see that that would work, right? If probability of island 4 is 4/28 and probability of island 3 is 3/28, that would satisfy kind of our criteria, okay? And this is just kind of looking at one pair of islands, island 4 and island 3, and seeing that balance happens at this point, right? So I guess I just want to check and make sure that this indeed is okay. All right. And okay, so this is the Metropolis algorithm for this kind of discrete island hopping example case. All right. So balance is achieved when the relative populations have this ratio. So probability island 4 equal to 4/28, and probability of island 3 equal to 3/28 works, okay? And in fact, will be kind of the only thing that works for all of the islands. If you find the kind of relationship between all of the islands kind of in this similar way, which you can do, it would be tedious, but you can do it, and you'll find that only the target distribution will satisfy the stationary distribution. Okay, and then the ergodic theorem says that if you let your Markov chain run long enough, so if the Markov chain is defined by this transition matrix, and if you let it run long enough, it will converge to its stationary distribution, which we can show is equal to the target distribution. Therefore, this Markov chain will effectively draw values from the target distribution, which is what we wanted. Okay, we can expand this to a continuous distribution, okay? So in the Metropolis algorithm, for a continuous distribution. okay? So basically, you have a target PDF, we'll say P, okay? Our target density, or target PDF, is, we'll say, is P, okay? We must have a symmetric proposal proposal distribution. Okay, because the way the Markov chain works is you have a random probability distribution and you're proposing values at random, okay? So we must have a symmetric proposal distribution, and this and so what this just means is that, you know, we propose values at random from a probability distribution. And symmetric means this. Okay, we propose values at random from a probability distribution, and let me include one more line, based on our current location. Right, this is the key difference between Markov chains and our previous methods, which generated independent values. Okay, here the values we propose are based on our current location. Okay, whereas before we're just proposing values from some, I don't know, a proposal distribution that was, you know, and every value we proposed was independent of each other. Here, all the values we're proposing are based on our current location, and our current location only. So the symmetric would mean that we'll say our proposal distribution is Q, will be that the probability of proposing Q prime given our current location is equal to the probability of proposing our current location if we were at the proposed location. All right, so this is the probability of proposing location x prime if we are at location xk is equal to the probability of proposing xk if we are at x prime. Okay, so the in the island hopping example, we used a coin flip, and that's symmetric, right? The probability of proposing island 5 if you're at island 4 is 1/2. And the probability of proposing island 4 if you're at island 5 is also 1/2. The probability of moving there is not the same, but the probability of just proposing the islands are the same, right? So the probability, so for the island example, probability of proposing island 5 if you are at island 4 is equal to 0.5. This is flip heads. And then the probability of proposing, not moving, but just proposing island 4 if you are at island 5 is equal to 0.5. flip tails. So that's a symmetric proposal. Is that okay? All right, so we have other examples of things that are symmetric. So, other simple symmetric proposal distributions. Could be normal distribution centered at xk, right? So if you're centered at xk, what's the probability of proposing x prime? That's right here, okay? Likewise, if you're centered at x prime, what's the probability of proposing xk? It will be equal, right? So the probability of proposing x prime given so the probability of getting x prime if you're at xk, so phi is shorthand for the normal distribution, okay? So letting mu is equal to xk and sigma is equal to sigma, some arbitrary value, is going to be equal to the probability of proposing xk if you center it at x prime, right? Because the distribution is symmetric. Is that okay? Yeah. Another example could be the uniform distribution from xk minus a to xk plus a, right? So if you imagine you have some xk and you go xk plus a and down to xk minus a, some arbitrary distance a, then then the probability of proposing a new value x prime will be the same, right? So if you propose x prime here, this is equal. I don't know how to draw this thing. Something like that, right? And it's the same. So you're just kind of shifting the thing around and whatnot. So here, the probability q of x prime given, bounds xk minus a to xk plus a is equal to q of xk given bounds x prime minus a to x prime plus a. So those are just some simple examples of symmetric proposal distributions for the univariate case. You can think of other ones as well. Okay, so anyway, Metropolis algorithm. So continuous case Metropolis algorithm. Okay, so your current location is xk. Use a symmetric proposal q. Okay, propose value x prime. Okay, you have your acceptance probability is going to be equal to the min of the probability of x prime divided by the probability of xk, right? Where p is the PDF of the target distribution. Okay. P can also just be symmetric. I mean, so not symmetric. Be proportional to the target distribution. So if you have some target distribution, but you don't know the constant c, the normalizing constant to make sure the thing integrates to 1, that's okay. Because that normalizing constant would appear in both the numerator and the denominator. So they cancel out. Okay, so p can just be proportional to the target distribution. Okay, so you do not need to find the normalizing constant. Okay, so this will be your acceptance probability. And then, and then your next value. So if you accept, the next value in the chain is x prime. And if you reject, next value in the chain is xk, right? So you just duplicate the current value. All right, is this okay? All right, let's I guess do a little example here. All right, so let's say our target distribution is the normal distribution with mean equal to 10 and standard deviation equal to 2. All right, so our PDF is going to be f of x 1 over root 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. Okay. So we can do that, via R. We can just use d norm for the density, right? D norm of x, mean equals 10, standard deviation equals 2. We can do that, right? All right. I know we know how to get values from the random normal, but we're going to pretend we can't, right? And we're going to say, we're going to do a Markov, we're going to do the Metropolis algorithm using a symmetric proposal to end up getting values from the normal distribution, okay? And furthermore, we can start off at a terrible, terrible, terrible location, okay? Okay, so we will use a symmetric proposal. All right, let's just use the uniform. Uniform from xk minus a to xk plus a. So we'll just pick some arbitrary value a. And that'll be our symmetric proposal, okay? Furthermore, we can have a terrible start location, right? Because we're familiar with the normal distribution, we know that most of the values in this case will be between what and what? Will be between what? 4 and 16, yeah. I mean, 95% will be between 6 and 14, right? So we know that we're not going to see values like 1,000. We're not going to see values at like negative 50, things like that. But excuse me. But in this case, because the normal distribution doesn't actually ever reach 0, okay? It reaches very small values, but not 0. We can start in a terrible location, and we will move in the correct direction, okay? So if, let's say we started off at positive 50, okay? In real life, we should never get values of positive 50 from this random normal distribution, right? But we're just going to start our chain at positive 50. And starting at positive 50, let's say our uniform proposal will be like values between, we'll go plus or minus 3. Okay, so we're starting at positive 50. We're going to propose values between 47 and 53. Okay, so let's say we propose 52. So we look at 52, we look at 50, and we say, the way we decide to move is we look at the probability of the proposed value. What's the probability of 52 under the normal distribution versus the probability of 50 under the normal distribution, okay? And the probability of 52 will be worse than the probability of 50, so we might move, but we probably won't, okay? On the other hand, if we propose 48 versus 50, okay, we'll look at the probability of 48, we'll look at the probability of 50, and we will find that the probability of 48, the proposed value, is greater than the probability of our current value, probability of 50. They're both really, really small probabilities. Like, they're both like not realistic values, but 48 is more realistic than 50, right? It's like less terrible than 50. And because of that, the Metropolis algorithm will say the proposed value is higher than the current value, so we are going to move with probability 1. Okay, so we will definitely move to 48. And at 48, we'll propose values at random from the interval 45 to 51, okay? And every single time we propose a value that's better, we're going to move in that direction. We might move in the opposite direction, okay? But we're less likely to move in the wrong direction, and we're more likely to move in the correct direction, okay? And so eventually, we're going to keep moving in more or less, most of the time moving in the right direction, and then until we get to kind of the region that's good, and then we'll be bouncing around a little bit in there. Does that kind of make sense? So let's just, I'm going to just code this up on the fly. So forgive me if it doesn't work the first time around here. All right, let's, okay, so let's say our, all right, so let's just look at d norm. All right, so we're going to have p will be a function of x, and it's going to return d norm x where the mean is equal to 10 and the standard deviation, oh wait, st is equal to 2. Okay, so we're going to have this. All right, and then so we can just try, you know, what's the p of 10? That it's a high value. What's the probability of 50? It's a very small value, right? You know, and then what's the probability of 52? It's even worse. What's the probability of 48? You know, it's a lot more likely than the probability of 50, right? Okay, so, but I mean, these are on the order of 10 to the negative 88, 10 to the negative 80. These are tiny, tiny, tiny values that should never happen in real life. Okay, so we can just say our current value, we'll start off at 50, okay? And then we'll have a RQ. RQ will be a function of our current value, and this is going to return one random uniform from what are the uniform distribution, min and max. Okay, so the min will be equal to xk minus a, and the max will be xk plus a, right? And this is, and then we'll just set a equal to, let's say, 3. Okay, and so RQ will be that, and we'll just say, okay, if I give you the value 50, what kind of value will you propose? And it proposes 49.7. If we try it another time, you know, it's just proposing random values between 47 and 53. Okay, it just gives us back one value. Okay, so we have our target PDF. This is our target, and this is our proposal. Okay. And all right, and then so let's just try this, right? So our chain, I'm going to just create results, and we'll start off with I guess we'll just we'll start off with 50. Okay, we'll start off with xk, and then we'll just say for I in, I don't know, 1 through 1,000. We'll just do 1,000 iterations. We will do, we'll call this x prime. X prime is going to be our random proposal. So we're going to just plug in our current xk. And then our ratio will be equal to the probability of x prime divided by the probability of our current value, xk. All right. And then so this ratio will be either greater than 1 or less than 1. So I mean, technically it should be the min between 1 and whatever this number is. But I can also just do, you know, are we going to accept this? U will be a random uniform value from 0 to 1. And this will be used to decide whether or not to accept, right? So accept is going to be equal to is u less than the ratio. Okay, so except is a logical value, right? It's going to be true, false. If u is less than the ratio, we will accept it. If u is greater than the ratio, we will reject it. Except will be false, right? So if the ratio is 0.75, u will be less than 0.75 of the time, and it will be greater than that 0.25 of the time. So this works as a way to decide whether or not to accept it with the probability equal to our ratio. Okay, and the nice thing about this is that if our ratio is greater than 1, u will always be less than the ratio. So I don't have to do the extra step of saying that the probability is the minimum of 1 and the ratio. Okay, u maxes out at 1, so it's okay. All right, and so now we need to store our results. So we'll say if except is true. So I can just do if except, but I mean, if you want, we can do if except is true. That's redundant. We can just say results I will be x prime. Otherwise, results I will be xk, our current value. Is that okay? Okay, and then the next value for the next iteration will be results I. Okay, so we're going to take whatever we stored, results I, and that will be the value we use for the next iteration. So actually, let me do results, and we will just create 1,000 of these values here. Right. So this is just a placeholder to store our values. Right? Does this make sense? So next iteration uses the latest result value. Okay. All right. Does that loop make sense? Maybe I'm giving you guys too much help here. Okay. But I just want to make sure this makes sense for the Metropolis algorithm. We just kind of did it on the fly. We said we're starting off here. We're gonna propose a value, right? RQ is a way to propose a new value. We're going to calculate the ratio, and then we'll see, do we accept it or not, and we'll go. Okay, so we got this. Our current value is 50. Our plus or minus is 3. We're going to create 1,000 things, and then we run. Okay, now we're done. Okay, let's take a look at. I'm nervous here. All right, let's see what our results look like. Okay, so let's plot results, and we'll say type equals L. Oh, let's plot from 1 through 1,000. Okay, and so we see we started off at 50, and in the beginning we just kept moving down, down, down. And then once we get kind of in this sweet spot zone of 10-ish, we kind of bounce around in there, all right? Which makes sense to me, okay? And so in the beginning, where we started off terrible, and it took us a while to get to kind of the realistic zone, that's known as the burn-in period, okay? Because oftentimes in a high-dimensional setting, where you have like thousands of parameters, or a bunch of parameters, you often have no idea what a good set of parameters are, right? So you just start off in this terrible, terrible location because you say, I don't know what parameters to use. So you just throw in some random values. You say, we're going to start here. And in the beginning, it does something like this. We're starting off in a terrible location. You start looking And the Metropolis algorithm, these Markov chains, will at least get you moving into the right direction until you're in this desired region. And then once you're in the desired region, you will bounce around and kind of stay within the desired region. Is that okay? Let's just kind of, so let's throw away maybe the first 100 values. Okay, oops. So if we do 100 through 1,000, let's go ahead and take a look at that. Let's make a histogram of the values 100 through 1,000. Okay, and it looks kind of normalish from what is that? Mean 10, standard deviation 2. I mean, we can do a QQ norm just to kind of see, right? We can run a bunch of normality tests. That looks reasonable, okay? We can do a Shapiro test and say, you know, do we have any reason to believe that these are not normal? Our p-value isn't the greatest, but it's around 5%. I mean, it seems, you know, kind of on the cusp of maybe it is, maybe it isn't normal, okay? It wasn't too hard. I could do like more. I can do like 10,000 values, right? And we'll just try this again. Okay, and then let's plot all these things, right? And we can see again, we start off terrible, and then once we're in kind of the region of what seems good, okay, that seems reasonable. We can make a histogram of the results from 100 through 10,000. Okay, that looks pretty normal to me. Breaks equals, yeah, that looks pretty good, I'd say. Not the greatest, but okay. So, you know, we have some issues in the tails. But that looks pretty good. The issue that we're dealing with here, though, is that our samples are highly correlated with one another, right? They are. There's a lot of. They're dependent, okay? And so, you know, if we look at the values, you know, because of this dependent nature that exists, we might have to throw away some of the values, right? So we might end up just filtering, you know, one third of the values, okay? So we can say the filtered values can be from results. We'll do 100 to 10,000, and then further filtered, we'll take our filtered results, and then we'll just do sequence, what is it, 1 through 9,000, and we'll just do bi equals 3. From 1 to 9,000, bi equals 3, and then we can take a look at our filtered results, see if that cleans it up any better. Take a look at our histogram of our filtered results. Yeah, it's hard to say, but That's what we have there. Okay. But overall, this is just the Metropolis algorithm. You propose a value, and then you use this acceptance ratio to decide whether or not to accept the proposed value. And if you don't accept it, you use your current value again. Okay. I kind of want to show what happens when we change what our proposal distribution looks like. Okay, so here, then we just do, we'll do 1 through 1,000. I think this will give us a little bit more resolution. So this was kind of our original plot showing kind of the first 1,000 values, right? I just want to show what happens. Let's say when I propose new values using our random proposal distribution, instead of 3, what if I did plus or minus 20? Okay, so if I'm at 50, I'm going to propose values between 30 and 70. And if I'm at 30, I'm going to propose values between 10 and 50 and stuff like that. Okay, and if I'm at 10, I might propose values as small as -10 and values as large as 30. What do you think that will, what kind of effect will that have on the Markov chain? Well, here, let's just take a look, okay? So, you know, we start off at 50 and we get down to 10 very quickly. All right, here, let's. So this was the previous plot. It took us, you know, up to iteration, I don't know, 50, 60, something around here to get us to the zone of 10. Oops. Over here, we get to kind of the zone of 10 very quickly. But once we're in the zone of 10, what do you notice? There's these flat lines here. What do these flat lines represent? Let's just take a look at the first 50 results. Okay, what's going on here? We got 50, 50, 50, 50. Why were we stuck at 50? Well, and then we get 32.218, 32.218, 32.218. And we see this thing where, you know, you get to a value, 13.732, and you're stuck at 13.732 for several iterations, okay? And then we get to 10.73299, and we are stuck there for 1, 2, 3, 4, 5, 6, 7, 8 iterations. And then we get to 10.49, and we were there for 3 iterations. What's going on? Yeah, because our proposal distribution is uniform from centered at where we are, plus or minus 20. If we are at 10.732, okay, we might be proposing values anywhere from negative 9 point something to positive 30.732, okay? And so if I propose a value like -9, -8, -7, those are all going to be rejected, right? If I propose values like 28 and 30, those are also going to be rejected because the normal distribution with standard deviation 2 really has values only going from like 4 to 16, or, you know, only within a small window. And so we're proposing values way outside that window, and those are all going to be rejected. And it's not until I propose another value like 10.49 that we're like, oh, that's a reasonable number, we'll accept it, okay? Because again, the goal of the Markov chain is to produce values that seem reasonable, or values that come from the target distribution, okay? And if we let this run long enough, then yes, indeed, the results would converge to the target distribution, okay? That's the ergodic theorem. It says if you let it run long enough, it will work. But we're going to have to let it run a long time because it's going to just like be rejecting a lot of values, right? Does that make sense? What's going on? Okay, what happens, and this is part of your homework, I guess this is the problem I did for you guys. What happens if instead of going plus or minus 3, I go plus or minus 0.2? We start off at 50 and we go plus or minus 0.2. What will happen here? Okay, so here we're like, we are moving in the correct direction, but even after 1,000 iterations, I'm still not even in the zone that's correct because I'm like walking a little bit too slowly, right? Here, we'll let it run for even longer. Okay, so it takes a long time, and then it gets to around 10, and then it wiggles up and down, and it looks like this. Okay, what's going on there? Here it's kind of the opposite problem. Okay. We're just proposing tiny little changes, and so almost every proposed value, like if we take a look at like values from 4,000 to 4,050, okay, what we see is, we're at 12.69, then we move to 12.72 to 12.85, and it seems like we're almost never rejecting any of the values, okay? Because, the probability of accepting is the probability of the proposed value versus the probability of the current value. And if they're very close to each other, their relative probabilities will be something like, well, it'll be better, and so you'll accept with probability 1, but the worst one will be like 0.98 of the current one, right? So it's like, if you compare, if you're currently at 12.69 and you propose 12.72, 12.72 is technically a worse value, less probable value than 12.69. But what's the ratio between d norm, or actually P is my d norm, 12.69 has probability 0.08, and probability of 12.72 has this probability. So if I do probability of the proposed divided by probability of the current, 12.6972, that ratio is like 98%, okay? So we're going to accept this proposed value with probability 0.98, okay? So we're almost always going to be accepting these nearby values. And so your line is just going to wiggle about, okay? It's going to just be this very small wiggly line, and yes, if you run this forever, eventually it will cover the entire target distribution and it will converge. But that's if you run it forever. And so there are you want to kind of look at your chain, and what you want to see is some random bouncing around. You don't want to see this small little incremental wiggling, because that's not a good sign either, okay? You don't want to be accepting 100 or close to 100% of your values, because it means the values you are proposing are not different enough for them to kind of border rejection, okay? So Okay. We have that. Okay. And you have some work in the homework that explores that. Let me bring on the next topic, and I don't know if you have any plans for graduate school or more schooling or whatever, but a lot of times if you look up Markov chain Monte Carlo, you won't see the Metropolis algorithm, but you'll see what's called the Metropolis Hastings algorithm, and that is a generalization of the Metropolis algorithm. And so for completeness, we'll cover it here. Okay, so this is the Metropolis Hastings algorithm. Okay, these are just different people's names. Okay, so Metropolis was a person's name whose name was on the paper that created the Metropolis algorithm. Apparently there's some speculation or some maybe history is that the Metropolis, that person himself did not actually come up with the algorithm, but like his students or the people he was working with did come up with the algorithm. But when you're in charge, you get to put your name first on the paper, and the algorithm gets named after you. Okay, anyway, there was a Mr. Hastings later on came and generalized the Metropolis algorithm. Okay, and so this is a generalization of the Metropolis algorithm. And it is that the proposal distribution no longer needs to be symmetric. Okay, so in the Metropolis algorithm, the probability of proposing a value if you're currently at this location had to equal the probability of proposing your current location if you were at your proposed value. Okay, with Metropolis Hastings, these no longer have to be equal. Okay, so some example could be for the island hopping example, island hopping with a either a biased coin or with a biased coin. So it's going to propose maybe the island, the coin lands heads 70% of the time. Okay, or something like that. Okay, or maybe you have a distribution that looks like this, or you put xk here, and I don't know, you're more likely to propose values that are larger than it. Okay, and so the only thing that changes is your acceptance ratio. Okay, the acceptance ratio becomes the min of 1 and the probability of your proposed value divided by the probability of the current multiplied by the difference or the ratio between the relative proposal probabilities. So this part's the same, it's just this is a new term. We add this. New term to compensate the different proposal probabilities. Okay. So if you're more likely to propose x prime given xk than you are to propose xk if you're at x prime, then that gets factored in here. Okay, so I don't know, should I write out the steps or is this okay? I guess I'll write out all the steps. All right, so the steps in the Metropolis hasting algorithms, steps in okay, so you have target PDF P. Let's say P of X, okay. Non-symmetric proposal distribution Q. Okay, and then so step one is randomly sample a value x prime from Q of x prime given xk. Okay, so this is your proposed value. Randomly sample or propose a value. Okay, find the acceptance ratio. Probability of the proposed value divided by the probability of your current value. So you're currently at value, I should say. And then I guess sample U to decide U from uniform 0, 1 to decide whether or not to accept the move. Okay. If U is less than acceptance ratio, accept x prime, and then your next value, x at k plus 1 is going to be equal to x prime. Okay. And if U is greater than the acceptance ratio, reject x prime. The next value, x at time k plus 1, will just be your current value xk. Okay. I think we'll wrap it up here for the day. Are there any questions? Good. Okay, we'll end here. You guys have some homework. Apparently, I did some of your homework for you. But please take a look and make sure you understand the topics covered in the homework. And have a good weekend. We'll see you guys on Tuesday.